The goals of this video are to get to know some symbols and definitions that we use in set notation. So you may have done some set notation before. We're just going to remember these symbols, and then we're going to try and use our new knowledge in a few examples. There's a Venn diagram about Venn diagram making, just for fun. Okay, let's start off with a concept that we know first, and that is the sample space. The sample space is the list of all possible outcomes. The sample space is the list of all possible outcomes of an experiment or an event, and we can use different symbols to represent that. I think that's called sigma. These other symbols here. So, for example, if I have a 10-sided dice, the list of all possible outcomes denoted by sigma, the sample space would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's pretty straightforward. Another symbol that we use in set notation is the subset symbol. So that's this one here, the subset symbol. It looks like a U lying on its side. And we use that when we're trying to show that something is a subset of another thing. So the example that we used in class was, if I have the A is equal to the set of all St. Clair's girls, students. Students, and if B is the set of all Year 9 St. Clair's students, then I could say that B is a subset of A, and I would write it using that notation there. Another way that I find is helpful when thinking about subsets is, if you can draw a diagram like this, there's A, the set of all students in St. Clair's, and B, the Year 9 students, is contained within A. That's a way of understanding the idea of a subset. Okay, we've talked about the complement of a set before, but I'll go over it again because it's some of us are finding it a little tricky. We use this symbol here, the A dash, to represent the complement of A. In other words, if this is A here, if this circle represents A here, then A dash is everything in our total sample space that's not a part of A. So sometimes we called it not A in the past. So let's look at an example for that. We're going to have the sample space is our class, our Year 9 Maths class. And let's say we define the set A to be equal to all students with brown hair. Then if all students with brown hair are in the set A, then all the rest of the students who don't have brown hair would be in A complement. So you might have students with blonde, black, red, colours of hair are there? Green, blue, etc. Anything except brown, any student with hair that was anything other than brown would be in the complement of A. Okay, so that's just a way of thinking about complement. Let me write it as that dash there. Okay, here's another symbol that looks like a little E, sort of curvy E, and it means is an element of. So say we had the set A is the set of numbers up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I could say that any one of those numbers is an element of that set. So I could say 2 is an element of the set A, where A is the set of counting numbers up to 10. I could also say that 3 is an element of A. I could say that 7 is an element of A. Okay, become clear why we need a symbol like this when we're doing examples later. This symbol here means a null set, or another way of saying it is an empty set. So example is probably the best way of understanding this. An example of a null set is, let's say the set of male students at St. Clair's. That's a null set because there are no male students at St. Clair's. Okay, another thing that you need to understand is when you see this here, n bracket A, that means tell me how many elements are in A. Cardinal number is just a counting number. So the number of elements in the set A. So here's an example. We've got a set called A. It's the set of numbers 1, 2, 3, 4, 5, 6. So the NA would be the number of numbers in the set. So there's 6 of them. So NA would be equal to 6. Another example, if A was equal to, say, the outcomes of tossing a coin. So here's the 2 possible outcomes, a head or a tail. Then NA is equal to 2 because there's two elements in that set. And you can see that we use this already for probability calculations, don't we? We count the number of things in the sample space for the denominator at the bottom of the probability fraction, and we count the number of things in the event that we're interested in for the top of the fraction, probability fraction. Okay, let's talk about intersection and union. This symbol here, it's like an upside down U, means intersection. And this symbol here, which is the right ways U, but it's a bit sort of fatter and flatter, means the union of 2 sets. So when I talk about the intersection of 2 sets, I'm talking about where the 2 sets overlap. So looking at a Venn diagram, say this is A here and B there, the intersection would be this space here where the 2 overlap. And remember, the other day when we were talking about it, we used the word and to describe it. So if we're interested in the intersection, then we're interested in things that are in both A and B. Alright, union is a little bit different because it means anything that's in A or B, or both. So if I draw a Venn diagram again with A and B, then I could represent the union by shading in the total region here. So anything that's in A, or it's in B, or it's in both, is in the union. So we use OR to describe the union because we're interested in something that's in A or it's in B. Okay, let's do a couple of little examples. I've set up two sets here. Here's the set A, which has elements 2, 3, 5 and 7. The set B has elements 1, 3, 5, 7 and 9. So if I want to talk about the union of A and B, then I have to list any element that's in A or B. So 1 is in there, 2 is going to be in there, 3 is going to be in there, 5 is going to be in there, 7 is going to be in there, 9 is going to be in there. So it's anything that's in either of them. When I talk about the intersection of A and B, I'm only looking for things that are in both. So I can see that 3 is in both, 5 is in both, and 7 is in both. So my intersection will be 3, 5, and 7. Okay, let's do a worked example. I think we didn't do this in class because I wanted you to actually do some practice and we were getting to the end of the lesson. So we'll do this together now in the video. A number is chosen from the set of positive integers between 1 and 8 inclusive. So I'll pull out what those mean in a minute. A is the set of odd numbers between 1 and 8 inclusive, and B is the set of prime numbers between 1 and 8 inclusive. So the question is asking us first of all to list the sample space. So I'm going to use my sigma to represent my sample space here. I'll use my nice curly brackets. Okay, let's look at what's in the sample space. It's the set of positive integers between 1 and 8 inclusive. So that the inclusive means that 1 and 8 are both in the set, and positive integers just means positive counting numbers. So 2, 3, 4, 5, 6, 7, and 8 are all in my set. Try and write a bit smaller. Let's have a look at A. What was A again? A is equal to the set of odd numbers between 1 and 8 inclusive. There's that word again. That means include 1 and 8 when you're thinking about it. So the odd numbers are 1, 3, 5, and 7. And let's have a look at B. B is the prime numbers. If you remember, a prime number is a number that's only divisible by itself and 1. In other words, it has no other factors. So 1 is generally not considered a prime number. It's a special case. So we start with 2 is a prime number. It doesn't have any other factors besides itself and 1. 3 is a prime number. 5 is a prime number. 4 is not because it has another factor besides itself and 4. It has the factor 2. 6 is not. 7 is, and 8 is not because they all have other factors. Cool, so there's our sets listed. Now let's list the set A intersection B. So remember, when we're looking at the intersection, we're looking at the overlap. We're looking at things, elements that are in both. So 3 is in both, 5 is in both, 7 is in both. So A intersection B has 3, 5 and 7 in it. A union B is going to have any number that's in either set in it. So it'll have 1, 2, 3, 5, and 7. What about A dash? Now, if we're looking at A dash, then we're looking at anything in the sample space now. Anything in the sample space that's not in A. So, if I use my orange pen, 1 is in A, so that won't go in A dash. 2 is not in A, so 2 is the first element in A dash. 3 is in A, so it's not in A dash. 4 is not in A, so 4 goes in there, etc. 6, 8. So basically I'm writing down anything that's in the sample space but not in the set A. Let's try B only. I'm going to go back to my black. B only. So what does that mean? That means things that are in B that are not in A. So we've already seen that there's 3 elements in common. So the only thing that's in B only is the element 2. Okay, let's continue. Now we're going to do some counting. We want to know n of A. So we've worked out what's in A, and there's 1, 2, 3, 4 elements. So n of A is equal to 4. What about the probability of A? Well, remember, when we're calculating probability, we look at the number of things that are in the event that we're interested in this case A, and we divide it by the number of things that are in the sample space. So we know the number of things in A is 4, and if we look at the sample space, there's 8. So the probability of choosing A would be 4 on 8, or in other words, half. I'm running out of space here. The probability, let's just do this one. The probability, do it in another colour over here. The probability of A intersection B. So we want to know how many things are in A intersection B. Well, we've already done this over here. There's 1, 2, 3 elements in intersection A intersection B. And again, we're going back to the sample space for our denominator. So 1, 2, 3, 4, 5, 6, 7, 8. So the probability of A intersection B would be 3 on 8. Okay, your turn. Exercise 9C. If you haven't already done 1, 2, and 3, just do 1 and 3. And I want you to do 4, 5, 6, 7, 9, 11, and 13. Good luck, and we'll talk about it next lesson.